So today afternoon, we have great speakers who are like top experts in like computational experiments and age-based modeling, especially there with like particular interest of a population. So that's the point I was expecting them to kind of educate us, because some of us are really expressing deep interest about the population and sociology. So yeah, so let me introduce you. We have two speakers, but they're on a common project. So first, Professor Ka-Yuet Liu is an associate professor of sociology at UCLA. She received her doctoral field in sociology from Nuffield College, University of Oxford. Her research applies data science methods and social network analysis to epidemiological questions. Her major test cases are the diffusion of health conditions that people don't typically associate with, network processes. And another note is that she is a local grown Hong Konger. She graduated from the University of Hong Kong. So this is really like the homecoming event, if I say so. So I'm really glad to have Ka for this talk. And another speaker, Ashley. So Ashley Gromis is got a new job. So you got a new job at Rand Corporation. But she worked as a postdoctoral research associate at the Emergence lab of Princeton University. She completed her PhD in sociology at the University of California, Los Angeles under the supervision of Professor Ka-Yuet Liu. Her research focuses on how social networks and local communities provide the social context for individual decisions and events that aggregate to form macro level patterns across space and time. So they are really like sociologists, but doing excellent job in computational and agent-based modeling. So I expect that there will be lots of things for us to learn. So without further ado, please join me welcoming Ka and Ashley. And floor is yours.
Thank you. Our talk is titled, it's about large-scale empirically calibrated agent-based model. This is a mouthful, it's a long title. But all it means is that we do some computational modeling that at the individual level. Usually in social science, it means like at the individual level, and then we try to use empirical data to inform the model so that we can explain some social phenomenon. So it is the agent-based modeling. I'm not sure how familiar you are with this technique. You can use that little show of hand thing on Zoom to raise your hand if you have read a paper about this, or you have used this yourself, or have some familiarity with agent-based model. You can click on that raise hand thing on Zoom. It will help me like gauge like what kind of audience I'm speaking to. Not much that I can see. All right, so okay, the slides is here. And yes, and it's my pleasure to be here, and we can go to the next slide, please. So agent-based modeling has been, well, some people claim that this is the revolution, or one of the revolutions in social science studies. A PNAS paper in the 2000 make this claim. Of course, like there's also all kinds of caveats, but that said, like we were so excited about agent-based modeling since the 2000. I'll wrap this talk up by telling you that I think we should still be excited about it. But there are very good reasons why we are excited about agent-based modeling, especially among sociologists. Sorensen is actually my academic grandfather. It's my PhD PhD advisors. So he was criticizing the more regression-based approach to the study of social phenomenon. This is a picture of a gas pump. The critique was that, like, if you have a regression model, like say you're trying to explain income, so explain how much people earn. So you have a linear regression model, right? And then you have all those regression coefficients. The models look like you're assuming like we got $2 from being a man, we got maybe $4 from getting coming from a rich family, and so on and so forth. Like extra $1 for you if you have a PhD. I'm not so sure about that. So this is the critique of the gas pump theory towards social science. It's a critique because the social world doesn't really work like that, right? We don't get different tiny bits of monies from different factors, right? What the social world that we experience consists of actors and the actions. Like people are acting according to the beliefs, according to the opportunities they have, according to the desire. So it's very different. It feels very different from like a regression model. So this dissatisfaction about like the formalism in like regression-based kind of approaches to social studies leads us to think about what kind of model is appropriate to model actions and actors, particularly the interactions among the actors, which would lead to various kind of social mechanisms. I'm giving you some examples here, like tragedy of the commons, like a vacancy chains, or other kind of feedback loop that we often see in social interactions. So what kind of modeling techniques can really capture this mechanism-based approach to the study of social issues would be something that we need the agent to have some sort of role in our model. So it's natural that if we think of agent-based model, is like a natural match. The agents, the desire, opportunities, and beliefs, we can like that explicitly put them into an agent-based model. So it feels like it is an appropriate method to study social phenomenon. And then other reason is that there's the issue of emergence. What we mean by emergence is that like things at the macro level, at a higher level, emerge due to the interaction at the lower level. And you cannot just look at the macro level alone and explain why there's such pattern. This is a picture of flocks of birds. We without understanding like what the individual birds are trying to do, like you cannot like really understand these macro patterns that which are often surprising. The issue of emergence, as you know, I'm a sociologist, is a key issue in sociology. Like my PhD was on the study of suicide, and Durkheim famously said that the suicide rate at the macro level is something that emerge, that cannot be reduced to individual psychological factors or risk factors. So this idea, the whole is greater than the sum of its parts, which come from Aristotle, is like one of the fundamental like idea in sociology. An agent-based model, because it's take into account or explicitly model the interactions between agents. This is a very appropriate method to try to understand macro patterns that emerge from this micro kind of interactions. And then, like, the title of this talk is spatially explicit, empirically calibrated agent-based model. Why spatial? Like, well, first of all, like, human interactions are often confounded or affected by space. Like, of course, we are on Zoom. It makes this claim a little bit weaker than it should be. But as we all know, before the time of Zoom, or even during the time of Zoom, that like what is said in the first law of geography, that everything is related to everything, but things that are closer to each other are more related to things that are far away. So, for example, like this is a regional computational methods group, right? Most of you are in Asia, maybe, apart from Ashley. So indeed, like space, even at the modern times, this is still a very important factors. So next slide, please. Next. So we are talking about spatially explicit agent-based model, and I'm just going to take you very quickly over the history of it. Like, at the very beginning, our kind of spatial agent-based model looks just like this. This is a famous, the famous game of life model. They were doing it not for, well, it was created for fun, basically. Like, they're this intellectual, and then they want to solve some puzzles. So they're not trying to publish paper. But that's how science was used to be done. Anyway, so the idea about, I'm using this example to illustrate that agent-based model actually is usually have this component of, we try to come up with very simple behavioral rules and then see what happened after the agents interact with each other according to these simple rules. So say in the game of life, there are like only these simple 4 rules. And then we would want to know, like, the goal of the exercise is to see what kind of society would emerge if the agents behave like this. So, like, if you only have one friend, you would die in this game. And then when you have too many neighbors, you would also die because of overpopulation. The ideal situation is you have 2 or 3 neighbors. And lastly, like, if there are 3 neighbors, and then the one in the middle here at the last paragraph would become populated. So people will move in there. So this rule sounds simple, but next slide, please. It will generate very interesting pattern just by having these 4 rules. I'm not going to talk about this model in details, but that's the beauty of agent-based model. You have very simple behavioral rules at the micro level, and then you can explain like the regularities at the higher level. So this little animation here is the famous glider gun and in the history of agent-based modeling. You can look it up yourself. So next slide, please. So the Schelling's model of residential segregation is another just slightly more complicated version of this kind of agent-based modeling. Some of you might have studied this in your coursework. But again, like this is the beautiful thing about agent-based modeling is that you have very, very simple behavioral rules at the individual level, but then you get something very unexpected at the macro level. So in this version of the game is that all of us are very, we are not racist, basically what we want to say. Most people, let's assume most of us are not racist. And then all I want is I don't want to be the very small minority in my neighborhood. So if there's only one of my neighbors that look like me, like the graph on the left, I will be unhappy, but I will be satisfied if there's only two of my neighbors like me. I don't have to be one of the majority group, okay? And even more, like if everybody is like me at the last, the right-hand side graph, I will be unhappy either. So this maybe would describe most of you. I assume like we're not against other groups. We just don't want to be the smallest minority in our neighborhood. But guess what? Like assume everybody is like this. You may imagine that the world would be salt and pepper, like people are mixing quite nicely and evenly across space, right? Next slide, please. The surprise is, even if all of us are so egalitarian, all we want is not to be the smallest minority in our neighborhood. When people are interacting, you would end up having residential segregation patterns that are very segregated. You will end up being in neighborhoods that the majority of people would be like you. Like you may be wondering why, if you haven't looked at the Schelling's model yet before. You can go to this website. I have put the link in the previous slides. I'm happy to share my slides as well. You can play it yourself, but the gist of it is like when some of the people move out from your neighborhood, like if you're blue square, if some of the yellow triangle people move out from your neighborhood, it would lead to a chain reaction of other triangles leaving the neighborhood as well. So and then the unraveling of mixed neighborhood over time would create this kind of highly segregated pattern. So it's not about individual ones, but the chain reaction, your action would lead to other people, what other people would do. So nobody wants this outcome, but it will be the outcome. If you don't believe me, you can go do the simulation yourself. Next slide, please. I'm going from very simple model to slightly more complicated model. This is one of my favorite examples in agent-based modeling. Like the model they propose are still extremely simple and they're all on the grid, but with very small change in the behavioral rules at the micro level, you can explain phenomena like how culture are formed, the change in wealth distribution. You can explain migration pattern, trade and war and that kind of thing. So and I'm not sure I have been able to, whether I have managed to convince you this is fun stuff. Like it's kind of like a game. but it speak to many core questions we have in sociology and in social science in general. Next slide, please. But those are the simple model, and the paper we will be talking about, Ashley will be talking about, are not of that kind. This kind of the paper we are going to present is one of this kind of empirical calibrated agent-based model. This is one of the more famous example. It is a huge model that is modeling the whole population of Portland, and then it's trying to use Portland as a virtual laboratory to study what happened if smallpox hit Portland, and then what kind of vaccination strategy would be the most effective. Does that sound familiar? Next slide, please. Because we have been doing those kind of modelings, those kinds of modeling in the past 2 years or so. You might have come across some of them, like they're trying to use whatever agent, whatever kind of modeling, including agent-based modeling, to try to study like the relationship between, say, vaccination strategies and COVID, or also like social distancing measure, and to evaluate the potential effects of so on and so forth. So it has been used, and it has been informative. For example, for example, masking can, how we, using agent-based modeling, we can quantify how much does having people wearing masks help in terms of how many days that it can delay the epidemic peak and so on and so forth. The examples I'm using from public health usually, because this is the area I work with, but agent-based modeling is not only something that is popular in public health. Like in business study, there are lots of agent-based modeling. We want to predict what would be the sales of this product. So agent-based modeling can help. There's a lot of agent-based modeling in economics, like trying to predict price action from the interaction from the individuals. So it's not restricted, even though if you're not thinking of going to be a public health specialist, there are other things you can do and other jobs that you can use agent-based modeling for. Okay, next slide, please. So I'm going to talk about administrative data in a bit. The kind of model I've been talking about, the most complicated version of agents-based model, which use like the Portland example I gave, and or the career model paper we just saw. You need to have some data on the population for you to build agent-based models. So the kind of one of the useful sources of data is administrative data. The administrative data, we just mean that data arrive kind of from the operation of some administrative system, like the IRS, like the tax agency, or any other kind of public sector agency like hospitals and so on. This is not collected for research purpose. The special case of it is census data. Census data is one source that people mainly rely on building this kind of empirically calibrated agent-based model I was talking about. It's not strictly an administrative data, and it's sort of collected for research purpose, and the the backbone of many of these models. But usually it won't have, say, I don't know, the distribution of COVID cases in different neighborhoods, right? Those data you need to link, you need to obtain from other administrative database, like the hospital authority database and so on. So next slide, please. I'm mentioning this because if any of you are interested in doing a project like this, I want you to know like there are pros and cons about such data, and or when you read a paper that use this kind of data, I would like you to know what the advantages and the disadvantage. The advantages are obvious, like you have the large N, like the models I work with have millions, at least millions of rows in my data set. Like when I first start off, like those models would take me 3 days to run when the computer power is not that great. Nowadays it's much faster, but you have a huge N. Like to me, like I got spoiled by this. Like I think a few thousand subjects are very little, very little data. Anyway, so there are other advantages, like usually the data can have last for a longitudinal. You have yearly observation of the phenomenon, and then it's cheap because the data are collected already. Usually you just need to apply for it and pay a small fees. If you're in Hong Kong, there are such data sets available in Hong Kong, but you need to go to Admiralty to, like, there's a special data center in Hong Kong that has a lot of administrative data, like hospital records and stuff like that. So they are available, they're already there. And then there are many disadvantages as well, like it's because the data were not collected for research purpose. It may not have the information you want, or the questions were not like asked the way that you wanted. Here in Los Angeles, researchers often want to study race and ethnicity, but those government officials would not use the same definition of race and ethnicity like a researcher would have, right? So there's all kinds of these other issues that I'm not going to go into, but I'm just trying to give you some background. Like there's a lots of data work going that had to happen even before you start making an agent-based model. Like I think the chunk of the time I spent for an agent-based model project Ashley can answer to that, but better than I do. I think like more than half of the time is in acquiring data before we even do anything. So maybe much more than that. And then next, please. Just a few words on spatial analysis. So incorporating spatial methods in your agent-based modeling opens up a lot of possibilities in terms of presentation of results, the kind of outcome you can measure, like as well as like robustness checks that you can perform on your modeling result. So I'm just listing some of the more standard spatial methods. We have applied it to our simulation results. The platforms can be, there's a lot of programs who can perform this kind of spatial analysis. I'm listing some popular one. I haven't talked about the kind of platforms we can use for running agent-based model because there are so many. So there are two kinds in general. One type is like programs that are made specifically for agent-based model. The easiest to learn one is called Let's No Go, which is the result of which is the residential model results that I have shown you. But there are so many others like the repass and stuff like that. But usually people nowadays tend to move towards using general programming language like R or Python to write the agent-based model because it gives the researcher more flexibility, and then there are toolbox that you can download. The Postdoctoral model was run with C++. That's tough because like the people may find it harder to replicate the result because it's not a common social science researcher kind of program, but they chose that because this is the fastest. Because the model is huge, it's a minute by minute interaction model, like it's gigantic. The lab has like 10 computer towers, and then they have multiple programmers in order to able to pull that project off. So those kind of constraints can restrict what kind of platform you would programming platform you can use. So depending on your project, I'm not sure you're ready to try to simulate Hong Kong yet. So, but those are the things that you need to be concerned with, like whether your computer can actually handle has the computational power for the model you want to do. Next, please. Okay, so let me sum it up for this range of from very simple model to highly complex model. On that point, I refer you to this awesome paper by Bruch and Atwell. This always has to be in your mind if you are thinking about doing an agent-based model yourself or when you're reading a paper. Whether you want to go for the simplest model that has only a few rules, and then the agents are interacting on a simple grid, or do you want to simulate a real world city? That's the question of high versus low dimension realism in the literature. The first question, the more complicated, the better. That one is easy. No, the more complicated is not the better. We would try to build the simplest model that is sufficient to explain the phenomenon you want to explain. This is the general idea in science, like in Occam with razor. The simple explanation is better than a complicated explanation. This is what we believe. The second question is trickier. It's the real question. Like the more is an agent-based model more realistic, the better that it is as a model. That is hard. Like it's real, because the more realistic, like if your agent and your world is more close to the real world, it seems to be a good thing, right? But it necessarily implies that you're making your model more complex, more complicated, and harder to replicate. It will depend on many parameters that you give in input into the model. So this dilemma here. We have this urge to make a model realistic because we say the point is to explain things that happen in the real world, right? Why don't we make a whole realistic replicate of our world, and then we can use it as a population sandbox. So a hand waving kind of answer to this question, to this dilemma, is that it depends on your research question. If your research question is to explore the macro outcomes, the potential macro outcomes of some micro interactions that you already know and clear. For example, like you have a beautiful micro level behavioral theory, like balance theory, like if my enemy, the enemy of my enemy is my friend, something very clear and concrete like this, as at the macro level. You want to explore what will happen if everybody acts like that, and then what's the macro outcome would be. Then you can have a the most simplest grid like the game of life kind of model would be ideal for that, because you don't need much more than that. But for the other kinds of research questions, like if you want to explore some macro outcome that have been observed in, let me give you an example from my work. Like we have found this cluster of autism in California. Like the rate of autism have clear patterns in California. We want to understand why. Without knowing a lot or inputting a lot of information into the model about the underlying population, like where do people live in California, how much they earn, and that kind of thing, like there's no way we can try to explain the spatial patterns of autism that we have observed, right? So for that kind of questions, we need to quite a lot of empirical realism in the data. And lastly, if you want to predict some outcomes for, say, a hypothetical policy change or social change, you probably also would need a lot of real life data to be input into your model. This is here, this the time I hand it over to Ashley, because this is what her paper is about.
Okay, perfect. Okay, so as Ka mentioned, I am going to talk a little bit about a paper that we worked on together that looks at the spatial clustering of vaccine exemptions, and I'm going to say a little bit more about what that is, and measles outbreak risk. And so I'm going to have to spend 5 to 10 minutes just doing a little bit of public health background, sort of on vaccines and California and what that looks like, just to sort of orient us to the question that we're studying, because I think it will make the most sense whenever we get to the actual agent-based modeling and some of the decisions we make in the population and sort of the models that we run. So to start, I think one thing that we sort of have to look at is the fact that measles incidence, so we're not really talking a lot about the measles now, but measles incidence pre-COVID was increasing in the United States. And this was really surprising because when we look at sort of the population vaccination goals for measles containing vaccine coverage in the United States, we were doing pretty good. We were about at where we were supposed to be to prevent large-scale measles outbreaks, and yet we were still getting a lot of measles cases. And so to think about why this was happening, we have to think about not only the overall population vaccine coverage, but where we're missing immunizations. And so just to give a little bit of background on this, so if you want to send your kid to school in the US, they have to be vaccinated for certain, they have to be vaccinated against certain diseases, one of which is the measles. All 50 states require that kids are vaccinated against the measles. The vaccine requirements, though, are set at the state level. It's not national in the United States. Every state gets to make their own requirement about what you vaccinate, what you have to have your kids vaccinated against, and also the allowable types of exemptions, or sort of the reasons that you can provide as to why your kids don't meet those vaccine requirements. And so one big category of these, which is increasing in the United States, is non-medical vaccine exemptions. So these are parents that are sort of submitting exemption requests on the basis of some sort of philosophical, personal, or religious grounds. Most folks equate these to a vaccine refusal. These kids are eligible to be vaccinated, but they're not vaccinated because the parent has not vaccinated them. These types of exemptions are not allowed in all states. They're allowed in most states, but it's not uniformly permissible across the US. The other category is medical exemptions. These are granted by physicians. They're usually granted on the grounds of like vaccine allergies or some sort of immunocompromised state that wouldn't permit the kid to be vaccinated. And these are allowed by all states. And I'm sort of giving you some background on this because we are going to, in this paper, Ka and I look at measles outbreak potential using California as a case study. And so we look at how exemptions, both of these types of exemptions, medical and non-medical, are distributed across the state. And so when we're thinking about where vaccination patterns, or sort of the distribution of vaccination patterns in California, there's sort of an interesting trend in non-medical exemptions throughout both the 90s and the 2000s, which we see on this graph. And so they're increasing over time. So the exemptions were relatively easy to get. And so there's a clear increasing pattern here. Also, they're spatially clustered across the state. So it's not just that they're increasing over time, but as you can see from the figure here, the areas that are shaded in green include schools that are more likely to have kids that have non-medical exemptions than the state as a whole. And so this is important because this means that kids that are potentially susceptible to contracting vaccine preventable diseases are located in the same areas throughout the state. And so this has consequences. There was large-scale outbreaks of pertussis, which is sometimes called whooping cough, in 2010, in 2014. And there was also a very large outbreak of the measles at Disneyland, which is a huge theme park that's located in Southern California that started around the end of 2014 and continued into 2015. And so this actually resulted in policy change in California. So the California legislature decided that they were going to outlaw parents exempting their kids for non-medical reasons for meeting the vaccine requirement. And this includes being vaccinated against the measles. So they passed this new policy in 2015. It went into effect the following school year, so the 2016 to 2017 school year. And what it did is it eliminated the new request of parents to have their kids exempted from the vaccine requirements for non-medical reasons. So you could no longer enroll your kid in school and ask that they not meet vaccine requirements. Importantly, though, it did not revoke or it did not eliminate the petitions against the vaccine requirements that had already been granted to kids who were already in school. So vaccine requirements are usually checked when you first enroll your kids in school. And so it didn't take away vaccine exemptions that were already existing in the population, but it did outlaw new requests from being made. And so if we look at the trends in the number of kindergartners entering school with these exemptions, there's a pretty clear effect of this new policy, right? So we see increases, the policy is changed, new policy in effect. These exemptions almost completely disappear from the California population. The interesting thing, though, is that medical exemptions, which only accounted for a very, very small fraction of the kids entering kindergarten in California up to this point, started increasing. And so there was a bit of a substitution effect. So potentially parents maybe that would have sought non-medical exemptions in the future were now seeking other routes to enroll their kids in school without fulfilling all the vaccine requirements. And part of this increase was also that previous, before, when you could get a non-medical exemption for your kid, there was very little clustering in medical exemptions across the state. It didn't look like the same map of non-medical exemptions, which you see in the top left here, which is the same figure that I showed you before. If you look to the figure to the right of that, very little clustering in medical exemptions prior to the policy change. After the policy change, though, we see increasing spatial clustering of these types of exemptions throughout the state of California, and they're often in the same locations or in sort of the same areas that we saw schools with higher rates of non-medical exemptions. So it's not just that these exemptions start to increase, it's also that the kids' parents, that I guess we should say parents, because they're the ones seeking those exemptions, parents are seeking those exemptions in the same areas that previously had high rates of unvaccinated kids. And so this raises important questions about how the increases in medical exemptions might affect measles outbreak risk, given that we've outlawed non-medical exemptions. And so we can ask, like, what effect does this have on outbreak risk? So we think about this policy as trying to increase vaccination in order to mitigate the risk of disease outbreaks. But what happens when you see increases in alternative forms of vaccine exemptions? And so sort of a secondary question to this is a question that really specifically looks at what happens when you have these kids located in the same areas. So if you have clustering of kids that are susceptible to being infected with the measles because they're unvaccinated, either because they previously had a non-medical exemption or they now have a medical exemption, how does that impact the risk of measles outbreak overall? And so this sort of gets us back to our original question of, should we be concerned with the overall level of vaccination in the population, or should we really be concerned about where we're missing those vaccines? Like, how much can that help us explain why we have measles outbreaks in the United States, despite the fact that more than 95% of the kids that are entering kindergarten are vaccinated against the measles? But if we want to answer this question, what's the effect of spatial clustering? We need to find a way to separate sort of the different trends we see, like what is the effect of the overall vaccination coverage in the population? What's the effect of the increasing trend of kids having non-medical exemptions over time versus like, what is the effect of having them spatially clustered? And this is really where agent-based models can help us, particularly large-scale empirically calibrated agent-based models, because it can help us answer questions that we're not able to observe in the real world. And so why agent-based modeling is so good for this type of question is because it's essentially a simulated experiment. So we can't, for very good ethical reasons, we can't conduct actual experiments on vaccination in the population. It's not ethical to vaccinate some kids and not others, or to have different population vaccination patterns in some areas and ask what happens if measles is introduced in the population. It's also it would be very impractical to try to even find examples of sort of differential patterns of vaccination and differential introductions of measles infections. And so what we must do is turn to these sorts of research tactics that can allow us to simulate what would happen in these cases that we just simply can't observe them. And so the other sort of thing that agent-based modeling can help us with is that disease outbreaks, and particularly the measles, because the measles is quite rare because vaccination rates are so high. It doesn't continuously spread throughout the population. It happens sort of more so in isolated outbreaks. They're increasing now, but there's an element of randomness. The measles can be introduced into the population. It can die out very quickly, or it can turn into very large outbreaks like we saw in 2019 in the US. And so part of agent-based modeling, as I'll talk through sort of in the methodology of our project, is that it sort of helps us preserve some of the randomness that's inherent in disease outbreaks or in other sorts of processes that are really dependent on how people interact in a population. And so when we can we run these simulation experiments, we introduce this element of randomness, we can also create counterfactual scenarios that we just wouldn't be able to observe in the real world. And so really, it allows us to ask questions of sort of what if, like what if medical exemptions did not increase after the policy changed in California? Or what if the unvaccinated kids were not spatially clustered in the population? And these are things that we really couldn't observe in the real world. But if we really want to think about separating the influence of overall population vaccination levels, or where people are, where unvaccinated people are clustered in the population, if we can't ask these what if questions, it's really hard for us to sort of separate the differential effects of these different factors. And so there have been some theoretical models of outbreak risk, and they've shown that spatial clustering of vaccine refusals or unvaccinated individuals can increase outbreak risk in a population. These models, though, they often use very theoretical settings. They look at populations that are sort of just distributed on a spare grid, or they look at just hypothetical levels of vaccination or hypothetical patterns of clustering in a population, or how people interact. And that can be really helpful for thinking about sort of theoretically how vaccination coverage can function in a population, or how disease transmission works. But if we really want to know, like, does the observed spatial clustering of vaccination in California increase outbreak risk? Is it really sufficient to sort of move the needle on how likely we are to have a measles outbreak? We really need to think more about, like, what are the observed real conditions of the population in California and vaccination there, because otherwise it's sort of like we have these theoretical ideas about the way that the world might work and about the way that outbreaks might happen, but they're disconnected from the population that we actually can observe. And so this is really where empirically calibrated models can help us sort of take these theoretical findings or these theoretical ideas and apply them to an actual setting in which we try to get data and we try to think about how things might actually, patterns of interaction or vaccine coverage might actually affect outbreak risk, like in a real world scenario. And so I'm going to spend a little time talking through the methods that we use in this paper. And sort of, this is the nuts and the bolts of the agent-based model that Ka and I looked at. I'm going to sort of give a high-level overview here. I'm happy to answer more specific questions about some of the things that we do. And I'm going to give you a little bit more on the specifics, but just to sort of start with a basic overview, we sort of did this in 4 steps. So first, we built a synthetic youth population of California. It looks very much like the real population, and I'm going to tell you more about that. What we varied is that we created 5 different scenarios of vaccination coverage in the population. So we created one scenario in which the population had vaccination coverage that looked like California vaccination coverage before the policy was changed. We created a second scenario that looked at the population after the policy was changed. So this is really helping us isolate the effect of the policy change itself using observed data in California. We also created 3 hypothetical scenarios that never occurred in California, but are going to really help us sort of tease apart the different reasons why we might see measles outbreak potential vary across different scenarios of vaccination. We then built a model that's going to simulate the transmission of measles in our synthetic population. And then we just counted the number of infections. So we sort of created a fake population in which to test this experiment. We created a model that used empirical data to allow measles to spread in the population. And then the actual outcome measure we use is quite simple. We just counted the number of measles infections that happened in each simulated trial of our model. And so first, I'm going to talk a little bit about the synthetic population. And so we created a population. And when I say a population, it sounds very grand. These are rows in a data frame. So just think about sort of any data that you would use where you're getting population statistics on something. It could be census data, it could be health data. It's just when you sort of distill data down to its essence, its rows in a data frame. And that's very much what we're working with here. So when I say synthetic population, that's really what you should be imagining. But the reason why we say it's synthetic is because we recreated a population that doesn't necessarily have exactly observed data from California, but is meant to look and act like the California population. So what we did is we started with block group, which is like a census unit in the United States. We started with block group population by age, sex, and race ethnicity. And so essentially just a population register. It has, a general spatial location, sex, and race ethnicity. We then assigned the kids to households. And so we did this informed with data on births that had happened in California to try to think about how big families should be and how much of an age gap there should be between siblings. And then we assign those households socioeconomic characteristics that might be associated with the type of school the child attends or whether they are enrolled in licensed childcare. And so some of these characteristics are like parental educational attainment or household income, or whether the mother works outside of the household. And then we assigned the kids actual point level locations. And so the map that you're seeing on the right is the population density of the synthetic population. It looks very much like the real population density of California. There's just over 9 million kids in the simulation. And so once we sort of have these kids spread out all over the state, we use the characteristics that we give them here to actually assign them real world locations that they can interact in. So again, these are just sort of synthetic, these are kids that are supposed to look like the real California population. And so we want them to be interacting in ways that would replicate the areas in which kids would interact in the real population. And so almost half of the kids ages 2 to 4 are assigned to go to childcare centers. And so we predicted the likelihood that kids would go to childcare centers or would need childcare outside the home based on the household socio-demographic characteristics I mentioned before, like household income, parental education, whether the mom works outside the household. We also, all the kids ages 5 through 17 in the population were enrolled in school. And so kids could go to public schools, they could go to private schools, they could go to charter schools, which is a version of public schools in the US, but they're not bounded sort of by traditional areas of enrollment. They have more parental choice in where the kid goes to school, or the kids could be educated at home in the home-based or virtual education program. And again, we use the household characteristics to predict the likelihood that kids would be enrolled in each of these types of schools. And so then after we had kids enrolled in childcare centers and schools, we also gave them other places that they might interact sort of in a usual week in the larger community, in the larger neighborhood. So kids were assigned to physician offices. And this is really important because measles infections, usually if you get the measles, you need to visit a physician. Like it's not something that like a common cold that you might get at home and just sort of like ride out and not be detected. Measles infections can be very serious. They have very serious symptoms. Almost all measles infections require a trip to a physician's office. And the important part of this is that other kids can be exposed to the measles in physicians' offices. And so it's actually been the case that in the US that a number of measles outbreaks, kids have been exposed in the physician's office when another parent has brought a kid in that has a measles infection. They didn't realize it, and so they didn't isolate the kid. Exposure occurs, and other kids contract the measles. So to replicate that in the population, kids who have the measles are assumed to visit the physician after they've been infectious for a few days. They might expose some other kids there. And so we built that into the population based on real locations of physicians' offices in California that we got from data from the American Medical Association. Kids can also interact in neighborhoods. So this is just sort of the census block group in which they live. Census block groups are an aerial unit in the US. They're sort of, they only usually include a couple of thousand households in the population. And so this is sort of a reasonable expectation maybe of an area that kids might interact with other kids during the day. Finally, we wanted to give kids sort of a larger community space to interact in. And so we put malls. We allowed kids to visit the malls in the simulation. And this is not because we think that malls are like very important vectors of disease transmission in the United States, they're sort of meant to represent larger community action. So this could represent like going to a more distant park, or going to a neighborhood swimming pool, or dance lessons, or sort of anything else that might happen outside of one's local neighborhood in which you would have close enough contact that you might be exposed to the measles. And so it's here, unlike the other sort of interaction settings in the population, we allow these to vary over time, just because, you know, you visit lots of different interaction points in your community, and we wanted to represent that in the population because we were trying to think about sort of like what would happen in the empirical, sort of like the empirical version of interaction. And so we allow this to change over time. I can, in the question and answer period, I can sort of talk more in detail about how we did this if anyone is interested. And so once kids were sort of in these locations and the population was set, we created 5 different scenarios of vaccination coverage in the population. And so we could observe vaccine data at the school or childcare level in California. So the California Department of Public Health releases annual data that looks at immunization levels in schools and childcare centers. Ideally, of course, you would see like what everybody's individual vaccination level is. That's not possible though, because that data is private and it's not shared for privacy reasons. And so the finest brain data we could get on this was at the school or childcare center level. We assumed kids were unvaccinated if they had a medical or a non-medical exemption, which is what I mentioned sort of in the background information for the talk. Infants less than 1 year of age were also unvaccinated because kids aren't recommended to get a measles vaccine until they're 12 to 15 months of age. And so then we had 5 conditions of vaccination in the population. So first, we had the scenarios as we observed them prior to the policy change in California, which we chose as 2014. That was the year before the policy change was introduced. And then 2018 was 3 years after the policy change took effect. So we wanted to know what measles outbreak potential looked like before they changed the policy, what measles outbreak looked like after they changed the policy. And then we created 3 hypothetical scenarios of vaccination, which helped us to sort of piece apart these different sorts of trends that happened in the population. What if medical exemptions didn't increase after the policy changed? What if vaccines were distributed completely at random? What if they were distributed at random, but still kept their increasing trend over time? What does measles outbreak look like in these different scenarios? And so after we assigned these exemptions in these different scenarios, we built a model of measles transmission. I'm going to walk you through a brief demonstration of what the model looks like. We used actual parameters of measles transmission from epidemiological studies to build this model. I'm happy to talk more about where we got any of these parameters or how we built this model. I'm just sort of going to give a brief overview of what the model looks like because I think it's more helpful for our purposes of understanding what's happening in the agent-based model. But so essentially, we randomly select one kid at the beginning of the model that's going to have the measles and potentially expose other kids. And so all the other kids are susceptible. Kids then can have contact in the 5 interaction settings I mentioned: household, schools, childcare centers, neighborhoods, physicians' offices, malls. It can be exposed to the measles. The actual infections happen probabilistically. Just because a kid is exposed doesn't mean they get the measles. And this mimics what we experience in the real world. Some kids who are vaccinated will be unlucky and get the measles anyway. Some unvaccinated kids will be very lucky and be exposed but escape vaccination, which is what happens in the real world. In general, though, the probability that an unvaccinated kid gets the measles is higher than a vaccinated kid. So it's probabilistic, it's not deterministic, but it's sort of what we would expect to see in the real world. So here, maybe just one kid acquires the measles infection. They then incubate the virus for 12 days, which is common for the measles. They continue, sort of the interaction continues on a daily time step in the population. Over time, more kids can be exposed. After kids spend about 3 to 7 days on average being infectious in the population, which is what happens in the real world. After that, they are considered recovered and immune. They cannot get the infection again. during the simulation trial, which measles immunity is typically assumed to be lifelong. And so we just we continue to run this model. Kids get infected, kids recover. We run it for 36 weeks, which is the typical length of the school year in the United States. And then at the end of this model, we just count the number of infections. And we do this 1,000 times in each of the 5 scenarios that I mentioned, just sort of have a better gauge of the stochasticity or the randomness that happens if we were to observe the measles in the real world. So what does this look like in practice? Okay, so first, I think it sort of, as we walk through the results, I'm gonna show you some of the differences in the scenarios that we model, because I think it sort of makes the most sense for interpreting the results. So first, we're going to look at what happens in a population that looks like the population before the policy change, and what measles transmission looks like in the population after the policy change. So both have spatial clustering of exempted or unvaccinated kids in schools. So the policy change did not eliminate spatial clustering, as we saw from the graphs sort of in the background information for the talk. There is a lower exemption rate in the post-policy change scenario. So the sort of eliminating the access to non-medical exemptions did decrease the total number of kids that had either medical or non-medical exemptions in the population. And you can see this in the age distribution, right? So if we're looking at exemptions by age, in the pre-policy change scenario, we see that clear increase over time in terms of younger kids having more exemptions than older kids. When we look at the post-policy change scenario on the right, we see clear sort of patterns in where kids have been checked for those vaccine requirements when they've entered kindergarten or the 7th grade in California, which is where vaccine exemptions are typically checked. And so we say, what happens when we allow the measles to spread in this population? And so we see that there's a small reduction in infections after the policy change, but it's only sort of marginally statistically significant. There's a very small increase in the number of trials that have, or I'm sorry, in the percentage of trials that have no secondary infections beyond that initial 1-seeded infection that we introduced into the population. So there's a marginally sort of significant higher proportion of trials that have no secondary infections after the policy change took effect. We also see a reduction in the percentage of trials that have sort of more than 10 infections. So when we're sort of thinking about larger outbreaks in the population, we do see a bit of a reduction after the policy change. Really though, if we look at the mean number of infections, it's reduced by 86% because there's an average of 50 infections before the policy change. That changed to 7 infections on average after the policy change. But this is because the distribution, like sort of the distribution of outbreak sizes in the population is very right skewed. Most of the trials, as you saw, about 60% of the trials from the last slide had no secondary infections beyond the initial seeded infection. Here, though, we have some trials, even if it's very few trials, that have hundreds and thousands of cases, which is sort of potentially representing, even if most times measles doesn't create large outbreaks when it's introduced in the population, we still do have these scenarios in which we get really large outbreaks that potentially manifest in the population. And so we can ask, what happens? Like, is the permission of large outbreaks in the population due to increases in medical exemptions after the policy change? Like, how much are we losing by seeing medical exemptions increase? And so we're sort of going to wave our hypothetical wand in the agent-based modeling world, and we're going to say, what if medical exemptions had not increased? So again, we still have spatial clustering. We haven't eliminated it completely because of those kids with non-medical exemptions that are still hanging out in the population. But we do have a lower overall exemption rate because we've said there's no medical exemption increases after the policy change. We've reset those levels back to 2014 before the policy change. We can see this a bit in the age distribution too. We have very few kids now in the age ranges that have been checked for vaccine requirements that aren't meeting them. And so when we look at the percentage of trials that have no secondary infections beyond the initial seeded infection, we actually see that it's very similar to the trial in which medical exemptions did increase. So when we compare the purple bars, which show the actual observed vaccine status in the California population after the policy change, and the orange bars, which show the hypothetical scenario in which we didn't have any increase in medical exemptions after the policy change, there's really no significant difference. The mean number of infections did decrease by about 50%. So we had, these sort of seem like small numbers. It's been estimated though that a measles infection costs about $33,000 on average to sort of, per an outbreak is $33,000 US dollars on average to bring an outbreak under control, which can add up to like a rather expensive public health crisis, even for very small outbreaks. So even though it seems like a 7 to a 3.2 reduction, it seems like small numbers. These can be very costly in public health terms. So we do really want to prevent additional infections where we can in the population. The thing is though, as you might notice, in any of these scenarios, whether we prevent the medical exemptions from increasing or not, we still have outbreaks that involve hundreds and thousands of cases. So we can sort of ask ourselves, what's going on here, right? Like, have we just underestimated the population vaccination coverage that we need to prevent measles outbreaks? Is 95% sort of the benchmark that we started with? Is that not sufficient to prevent outbreaks in the population? Or is it the increasing exemptions over time? So we know kids are likely to interact with other kids of the same age. We've seen this from a lot of network studies. Is it just that, if kids of younger ages have higher rates of the exemptions, we're more likely to get outbreaks in the population because they're interacting with each other? Or is it really the spatial clustering? Is it those areas with schools with higher rates of these kids having exemptions that's really creating overall lower population protection against larger outbreaks? And so again, we're sort of going to enter the hypothetical with this agent-based model, and we're going to say, okay, what if these exemptions were not spatially clustered? And we can have two different scenarios of this, right? So we can randomly distribute the vaccinations, or I'm sorry, the exemptions across the population. We can eliminate the spatial clustering across schools. We can keep the exact same exemption prevalence that we had in the pre-policy change population. So I haven't made the population as a whole more vaccinated. I've kept the same level of vaccination pre-policy change, but I'm going to shift the age distribution here. So in the scenario on the left-hand side, I'm going to retain the number of exemptions over time. So younger kids are so more likely to have exemptions. This could be sort of, if it's just the increasing trend over time that's increasing outbreak potential, it would be captured in this scenario. On the right, again, same number of exemptions, but I'm going to distribute to them completely randomly across ages in the population. And so this is really going to help us tease apart this question of, is it overall population vaccination? Are we going to see the same outbreak potential that we saw in the pre-policy change scenario when exemptions were spatially clustered? Is it the age trend, which is the scenario on the left? Or is it just, can we eliminate it if we eliminate both the spatial clustering and the age trend, which is the scenario we see on the right? And what we find is, somewhat surprisingly, that there's actually fewer trials when exemptions are distributed completely at random across the population that have secondary infections beyond the initial seeded infection. We find that there are actually a slightly higher percentage of simulation trials that have very low numbers of infections. And this is likely explained by sort of a network effect of a targeted versus random attack. So when exemptions are distributed completely at random throughout the population, it's easier to initially find an exemption to continue the infection, but you're not finding large clusters of them. So you're not getting maybe as many large exemptions, or I'm sorry, large outbreaks, but you are seeing a bit of sort of a heightened initial transmission in the population. This actually doesn't sort of carry over into observed outbreak risk for a number of reasons, which we can talk about more in depth at the end. But sort of as the initial results on the other slide sort of hinted at, what we get here is when we look at the distribution of outbreak sizes across the different scenarios in the population, we see that when when the exemptions are completely distributed, or when they're distributed at random in the population, either by space and across ages, we don't see the large outbreaks that can train hundreds or thousands of infections the way we did when vaccine exemptions were spatially clustered. So we're seeing a clear difference here, even just setting aside the policy change that eliminated non-medical exemptions. We see that there's much larger outbreaks when we have spatial clustering and exemptions than when we distribute them at random throughout the population. And so when we're thinking about what we can,
it's 10 minutes left. So shall we leave some time for questions?
Yes, okay, I'll wrap up really quickly. So just sort of here, these are things we've talked about before. We see that spatial clustering is more consequential than time trends. It's not just your overall population vaccination, but where where the kids that aren't vaccinated are clustered in the population. And it's also really can help us evaluate effects of policy change. So maybe it helps us increase overall population vaccination levels a little bit, but it doesn't eliminate spatial clustering. Just sort of some caveats here. We're not predicting outbreak locations or sizes. It's a stylized example. We're making some assumptions about measles vaccination status, and we're just letting it spread in the population. But we're sort of trying to think about what is the overall potential of outbreaks. And so to think about sort of the larger question that we started with, which is why we use large scale empirically and calibrated agent-based models, is because we can think about population level risk and sort of answer questions about the effects of policy changes before we change the policy, or in areas that we may not be able to observe it in like a randomized control trial or experiment population. And we can sort of anchor our simulations in real world conditions, think about who we're likely to interact with in population in a way that's sort of more realistic than theoretical models, of course, more simplistic than real world. We can never fully get the real world in our models. And these can be particularly helpful in cases that we want to know what the effect of something is when really social interaction or sort of processes of social or biological contagion or sequences of interaction over time is really important for understanding overall outbreak risk. So here, we're happy to take your questions. I've listed the paper that these results that I've talked about today come from, in case you want to see sort of a more full explanation of the population or the model, and my contact information, of course, if you have specific questions about the population. But I think both Ka and I are happy to take questions that you might have about this simulation model or the other sort of larger questions about agent-based modeling as well.
Thank you so much for Ka and Ashley for this very thorough talk about starting from what agent-based modeling does and specific applications for measles outbreaks. So I'll open up the floor for questions to them. Okay, Baichi.
Hi, Professor Liu, and Ashley, thank you for your wonderful talks. Actually, I want to ask questions about my project. I recently focused on the online instability in Hong Kong district, and one of the classic theories we leverage is also the social contagion theories that you mentioned above. So I just wondered, is there any classical contagion models that you think might be helpful for my project? And I also have another question, is that I also see a paper talking about the disease controls, and I also wonder, I also want to study the uncivil behavior control. So I also want to learn about some classical control models. Yeah, thank you.
So your project was about, I missed that part. You want to study the contagion of what was the
online incivility, uncivil behaviors.
Online incivility.
Ah, in syphilis. Okay, so the standard model for that would be the threshold model. I think that's the first one that came to mind, the Gannoveder threshold model. Like how much you do the likelihood for you to do certain thing depends on the proportion of your friends doing certain things. That's the first model that come to mind. You can type into the chat what the people you may want to look at. Disease model, there actually you have the model actually talk about the SIR model at the typical. It's usually how you start. Yeah.
I think the project, I think the participant that I want to study is the people talking on the online forums. Yeah, they can discuss, exchange each other's opinions, and they may lead to some uncivil behaviors online.
Right. Well, the individual level model can be very simple. Like it's you can think about, it doesn't have to be very complicated. But you want to specify how they would interact. And there's also a question in the chat from Han earlier that about the computational complexity. Ashley, maybe you can take that one.
No, you're right. So the question was, a more realistic agent-based model involves more parameters, more complex functions that sort of describe the agent behaviors. Is it more computationally expensive? Definitely. So it's a trade-off sort of between what you want to make sure you're representing the behaviors that you think are really going to be consequential to the outcome that you're studying. But the more parameters that you put in, the more different categories of interaction or types of interaction or sort of demographics of the population, the more lines of code you sort of have to write that control those behaviors, and the more computationally complex it becomes. And it has been a challenge over time. Sort of as Ka mentioned in the beginning of the talk, you can spend hours, you spend a lot, you spend weeks, months, a lot of time sort of getting your model to sort of to that right level of realism versus parsimony that you can get to run in your computational setup. And there really is a trade-off that you sort of have to, at some point, that you have to sort of make between what is the maximum number of parameters I can get in there versus what are the most important parameters that will run in a reasonable amount of time on my computer, or even in like a remote sort of parallel computing system. And it can really be a balance that you need to strike and that you just need to work out sort of in practice.
Thank you very much for the answer.
I might have a question. So I know like this is the very specific application to the state of California. And I know that the goal for agent-based modeling is not to like generalize empirical, like finding as empirical research does. But I was still wondering, like when I was listening to the talk, what if the Measles break happens in other states? And also California has its own characteristics, so it needs some specific parameters that require to model like these outbreaks. But for example, like Kentucky, or I'm not really generalizing such features for like different kinds of states. But so what would happen like if we just model like this kind of outbreak in some states that are totally different? It's not totally different, but may require some other types of parameters to model and things like that. So have you thought about like this kind of like heterogeneity in terms of agent-based modeling? I think that's also pretty like methodological topic about kind of reaching to the conclusion based on the parameters that we have for specific state and things like that.
That's a great question. So we chose California because they have good, they're one of the states that have good vaccine data. They also had a lot of the exemptions that they were speaking of because of their policies. You're right, though, that if we try to apply this to another state, we'd have to take their policy, their vaccine policies for schools and sort of get empirical data on those states. In general, the effects of spatial clustering, you would expect, they've been pretty consistent in theoretical models, in our models in California, in models other folks have done, folks have done in other states. But if you were to make a model for the entirety of the United States, you would not only have to account for sort of you might have to trade off some of the specifics that you could represent in California for the heterogeneity across states, which you're mentioning, which is sort of another layer of complexity. And you'd really have to think then about how much of the differences across states you preserve versus some of the other parameters that you put in the model. The California, the population, we really made it to reflect the California population. Some of the main conclusions might hold, but you're right that you might get different patterns of transmission based on the different clustering or types of exemptions in those other states. And really it's sort of an empirical question. If you want to do the whole United States, you would have to sort of, you would have to strike this sort of balance and think about a more complex model that preserved these differences.
Yeah, so there's a question in the chat from Han again. I would recommend just playing with net logo. That's how I started. That's more than sufficient as an introduction. Just download that logo or use your web interface and just play with it.
Cool, thanks. Yeah, so I'm asking that question because in computational social science and agent-based modeling, it's a part that I myself do not find a lot of resources compared to, say, if you want to learn machine learning or statistical analysis. So this is always a puzzle I have for my own learning before, and also now being a teacher, I always have a hard time recommending stuff. So yeah, so thanks for the recommendation on the net logo. And Ashley, do you have anything to add? Sorry, I interrupted you, I think.
Oh, no, all good. So there are actually, depending on the statistical programming language you use, there are some R packages that are just tailored to sort of agent-based modeling. If you shoot me an email after the talk, I'm happy to send you some of those. And then a sort of a fun way to learn can be if you can find some papers that sort of have very basic simulations and that have good appendices that will sort of walk you through what you did. What they did, and then if you sort of, it allows you to sort of have some resources to recreate a basic simulation, which then you can sort of take those skills and apply it to whatever sorts of problems or parameters that you're interested in working on.
Thank you so much.
Okay, so our time is up now, 2 p.m. So please join me appreciating the two speakers today. And for this particular workshop, so we will have break, so tomorrow, Saturday and Sunday. And Sunday we will have lunch together. So I will see some of you there. Yeah, so this is for today. So thank you, Ka and Ashley. And see you guys.
Thank you.
Bye-bye.
Bye.
Thanks.